that demo is about tracing and sequence diagrams. And I will use code real-time for this demo, but like I said in the beginning, this also applies for model real-time users since the traces are produced by the target RTS, which is the same in both products. So there is a new sample here called tracing that is present in the GitHub repository for code real-time. And we created this sample to showcase almost all features that apply in the tracing area and sequence diagram area. And this is a simple ping pong style game where we have a top capsule that has two optional parts, player 1 and player 2. The top capsule runs in its own thread, and player 1 and player 2 has also their own threads. If we check the TC file here, you see that we have the main thread that runs the top capsule. We have player 1 thread running player 1, and player 2 runs by player 2 thread. So now let's start by just running this sample, and I do that just by right-clicking doing run. I don't provide any particular arguments to it. And you can see that it plays 3 rounds of ping pong, 10 balls per round. In total, 30 balls were played. And in the previous demo, when we did tracing, we always had to add some arguments to tell the application that it should capture a trace. That is not done here, and you can still see in the target folder that a trace file was produced. So then you may ask, how did this happen? Well, the answer is if we open the top capsule here and we search for configure, we find this code in the initial transition of this capsule. So there is a new API in the RTTracer class where you can call isConfigure. So this function returns true if tracing has already been configured, for example, on the command line. And if it's not configured, then you can now programmatically configure it yourself by providing the trace configuration file here programmatically. So this makes it possible to fully control tracing also from the code, not only from the command line and from debuggers, like we have shown in previous demos. So here I'm passing this trace config file that is present next here, and that's the default simple trace configuration that just says I want to have nanosecond precision for my timestamps, and I want to capture the time when a message is received and the time when a message is handled, and nothing more. If we look at this trace file then that was captured, we can see some news in this trace configuration comment that is printed in the beginning of the trace file. So this, for example, line 19, we have now added arguments. So here you can see what command and arguments were passed to the application when it started. And that's quite useful because it's not uncommon that the arguments you provide to an application actually affect how the application behaves, and hence what trace events that are captured. There are also some news here under the trace file. We have now a new name property. So here you can specify the name of the trace file. So by default, it's called .trace, which means the trace file will be called .trace.rtrace. If you want, you can also use variables here. It's mentioned in the documentation. And those variables can, for example, expand to the current timestamp. So you can ensure that trace files always get unique names. There is also a new property called overwrite. So by default, a trace file with the same name overwrites any other name, file in the folder with the same name. But if you set this to false, then it will not do that, and instead it will give you an error message saying that you are about to overwrite an existing trace file. And so this is something you can use in case you would like to avoid losing previous trace data by mistake. If we scroll down here, we can also see some news in the actual data that we capture. For example, for each instance, we now capture in this JSON object what thread is running that instance. So here we can see that the timer actor instance is run by the time thread. We have our top capsule run by the main thread. We have player 2 run by player 2 thread, and player 1 run by player 1 thread. And this I will show you later why this is useful to have. There is also some more information here that I will come to later. But for now, just let's open this in the sequence diagram. So in the previous version, we only supported these straight arrows, which represent asynchronous message communication. So something is sent and received, but there is no synchronization between those points in time. But as you know, Model RealTime and Code RealTime also supports synchronous communication by using invoke and reply. And this sample uses a number of such synchronous message calls. So here, for example, we see increase count. This is shown here with the same line for the call, but then there is a dashed line showing the reply. And this is the same notation as is used in UML sequence diagrams. And this small rectangle here that you see on the receiver lifeline shows that the sender is suspended while the receiver is managing or handling that message, and then the reply comes. In this case, this increase count doesn't require any reply data. It's like a void function. That's why the reply is implicit and it's dashed without any label. But if we scroll down, we can see another example here where we are calling get count, and this, as you can tell from the name, is some event that has a corresponding reply event. And here we can see that this corresponds to a reply event that replies with integer 10. Then you see it on the dashed reply line like this. You can also see in this tooltip the time diff. So this shows the difference between the time when an event was received and when it was handled. So it basically shows that this transition took 2,500 nanoseconds to execute. And that can be useful as a quick way of finding trouble or finding bottlenecks, why some parts of the application is too slow. There is also now navigation possibilities. Already before, you could double click here on items on the diagram and jump to the corresponding place in the text file. Now we also support the opposite. So if you, for example, go to this instance here and you right click and do open sequence diagram, that lifeline that corresponds to that instance will be highlighted here with the yellow color. It also works on lines. So if you click on this line, for example, for the message and open sequence diagram, then the corresponding message lines will be highlighted here in golden color in the diagram. So that's useful for, especially when traces are big, so you can easily jump between the diagram and the text file back and forth. If we scroll down, we also see some notes. So previously, the only note we had was when tracing was paused. So when you turned off tracing, then we printed this note so that you can see that during this time, no trace event were captured. And then when it was turned on again, then we start capturing events. So something new here is that we also now capture the time when this happens. So you can know it precisely at what point in time tracing was paused. But scrolling down either further here, you see that there is now also a possibility to write custom trace messages. So here, for example, I have my own custom trace message that I have written myself. It looks like this in the trace syntax. So if we look at how that was done, we can scroll up here to find this API. So there is a new API in the AutoTracer class called Note, where you can pass a text string, and when you call that, then that text string will be printed to the trace. And this is very useful because you can use it for example, assertion failures or runtime errors that occur, and basically make any arbitrary text visible in the trace and with an exact timestamps that correlated to all the other things that happen in the application. Yes, I think that's most of the news. Well, maybe I should also mention sorting. So now, previously, we used to only by default capture the time when a message was handled. So this was by default true, but this was false. I mean, the property that controls capturing of the reception time. But that had a bit of a negative consequence on the readability of the diagram. I can show that by turning this to false, and then you can see how it looks. So if you scroll down to that same message as you saw, now you get the reply before the invoke. And the reason for that is, of course, that the reply is completely handled before the invoke is handled, because the invoke has to wait until the reply has been handled. So even if this is technically correct, it's not intuitive and not the way how users prefer to read sequence diagrams. So that's why we have now changed this so that by default, you have this true, and that makes synchronous messages appear in the logical way how you usually want to have your sequence diagram look. There was also one other small improvement that I cannot show in this sample, but I need to use another one because this sample doesn't have an external lifeline. But if I find one that has, like this one, I can show a sequence diagram here that shows this purple lifeline. So this is a lifeline that represents the environment of an application. So in this application, there is an external port where we are injecting events when a TCP request comes, and that is then now shown clearly with this purple color. So here we can see all the colors used. So purple means external lifeline. We have the green means the top capsule, top lifeline. We have the light blue ones that represent the things that are built in, provided by the target artist for system and timing. And then we have all the dark blue, which are all the instances that your application create by itself at runtime. So let me go back to this sample again, and now I will talk about Google Trace Event format. So that is a format that is used by many for performance analysis. I think it originally started when they created the Chrome web browser. So Google created that format to measure performance and use a nice trace format to be able to do that. But it has since been adopted by many other applications and trace visualizers as well. And we have on our GitHub page, there is a special GitHub page for our trace where we are providing the source code for our trace parser. So by consuming that GitHub repository, you can actually write your own script that reads these files and perform your own custom analysis of it. And here under samples, you have plenty of samples which we have written to show you what you can do. For example, you can use it for converting it into different visualizations. You can, for example, here's a script that measures the performance, it finds the transition that is taking the most time in your application. And all of these are very simple and are just examples. And one example we've also created is this Google Trace Event format, which converts an RTrace file into the Google Trace Event JSON format. And to run that, you can just go to a terminal and run it like this. So here I've cloned this GitHub repository, and I need to provide the source file, which is this file you see open in the editor, and I give you an output path to where it should save the JSON file. And if I open that, you can see it's a quite unreadable JSON format. It's not meant to be read like that, but instead you should open it in a trace viewer. The THEA trace viewer, some of you are familiar with, it can read these files. You can also use the trace capability that is built in the Chrome browser. So you just type Chrome://tracing and you get this UI. But actually this is a bit of a legacy UI now. There is a new, more modern UI called Perfetto, which has its own website where you can load these files, and it has better performance and can manage better files and has many more features than the legacy trace viewer. So here you just open a trace file by clicking Open Trace, and I will pick the file I just generated. And this will then open this trace in the Google, in the Perfetto trace viewer. And this shows the same information as you saw in the sequence diagram, but in a completely different way. So here you have a timeline from left to right. The application starts to execute here at time 0, and then at 3 seconds, it stops executing. You see the top executable here, and if you expand it, you can see all the threads below that executable. So here we can see that there are the main player 1 thread and player 2 thread. If you press special keys here, you can zoom in to see details of what is happening in each thread. And here you can see that each event is correlated time-wise to the other events. You can precisely see when something begins and when it ends in the different threads, since it's overlaid on top of each other. And within each thread, nested rectangles are used for showing synchronous calls. So here is an example where when we get the ball event, we make a synchronous call to increase count. And since ball is suspended, when that is processed, it gets nested below here. So it's like a traditional call stack with boxes nested below each other. On the top, you can also see, if I zoom out, you can see these unnamed slice track. So here you can see those notes that I showed in the file. So for example, here you see at this particular point in time, tracing is paused, and that explains why there are no trace events for the rest of this period here. But then tracing was turned on again. If we zoom out to the very end here, when tracing has been turned on, we see some additional things coming. And here is the note that I showed in the diagram where my custom trace message is printed. This is quite useful because now you can put your own custom messages and you can correlate them to everything else that happens in your application. And of course, if you click these boxes here, you get some additional information about when things start, how long it takes, and so on. There are many, many more features in this tool that I cannot cover here since we are soon out of time. For example, you can use SQL for searching in your traces. You can use some data exploring and different kinds of metrics and overviews that can be quite useful for both understanding how our application behaves and also for troubleshooting performance problems. But I think that was what I want to show. Any questions about tracing or sequence diagrams?